Okay, so we're going to start looking at the periodic table. So the periodic table of elements did not just start out fully formed. It's been developed by many scientists over the years. And we're going to look a little bit at the history as well as dive into how it's broken down and how it's organized. So the periodic table is kind of our way of organizing all of the elements that we currently know about. Back at the very beginning in Aristotle's time, there was earth, air, fire, and water. And yes, if we added heart, we could have Captain Planet. But since then, we have identified 90 naturally occurring elements, and about 28 others have been created in a lab setting. So the periodic table is organizing the elements in a very particular way. We know a lot of information about an element just based on where it is on the periodic table. That allows us to predict what physical and chemical properties there are just based on where that element is at. If we go back to the 1800s, we have Johann Dobereiner, who noticed that the atomic weight of strontium was midway between calcium and barium, and that they all had similar properties chemically. So he then noticed another triad, chlorine, bromine, and iodine. And then there was lithium, sodium, and potassium. So what he proposed was that nature contained these triads, these groups of three. And he noticed that that middle element had properties that were kind of an average of the other two members when you looked at them in order with their atomic weight. And so this thing that he proposed is what we refer to as the law of triads. We fast forward about 40 years and we get John Newlands, who was an English chemist, and he took the 56 established elements, he grouped them into 11 groups based on their physical properties that were similar. And what he noticed is that many pairs existed that were different in their atomic weights by some multiple of 8. And so he looked to the music system and realized that if we looked at these 8, we have octaves. So what he did was he published his version of the periodic table, and he proposed what we call the law of octaves, which is referencing, of course, to the musical scale. This law states that any given element is going to exhibit similar behaviors to the 8th element following it on the periodic table. Now, that leads us just a few years ahead to one of the two people who could arguably have been said to have come up with our modern periodic table. Dmitri Mendeleev, in 1869, beat the other gentleman by 1 year in publication. He created the first accepted version of the periodic table, and he grouped these elements according to their atomic mass. As he did so, he realized that there were these families created that had similar chemical properties. Now, really what made him kind of the father of the modern periodic table is not because he was great at organizing, but because he was smart enough to not only leave blank spaces in the table for things that he hadn't yet seen, he also predicted some elements. And when they were discovered, that gave him some great credibility. So his periodic table looks kind of like this. It's organized according to increasing atomic mass, not by the atomic number, but by the mass. That meant some of the elements were out of order, but with just 56 elements, the biggest thing, you see those gaps, that was his biggest contribution, recognizing, I don't know, but it looks like there might be something that needs to go right here with that 44, or maybe there's something that should be here. So he noticed that there were some gaps, and he was predicting elements to come. That leads us to Henry Moseley. he took Mendeleev's periodic table and said, if I organize it by the number of protons, which he determined using an X-ray analysis process, instead of by using the atomic mass. So I look at the atomic number instead of the atomic mass. A lot of the issues that they were having with it went away. So he just rearranged it. And that takes us to kind of that modern period, as you can tell with the photo here, more modern picture. Glenn Seaborg decided that, hey, if I take the lanthanides and the actinides and I move them down here to the bottom, all of these elements here have their last electron into the F sublevel. So we're looking at the F sublevel. That creates a lot of the bottleneck, and it allows these D sublevel, these hot pink ones here, to stay in place, and that creates less chaos in the long run. So he created these two table pieces here at the very bottom of the periodic table. So when we look at the periodic table, it's divided into three main categories. There's the nonmetals, which here are the bright green. You've got hydrogen, helium, and this triangle right here. We've got the metalloid, that is this hot pink right here. And everything else are part of the metals. So when we look at metals, they are good conductors of heat and electricity. They're shiny. And they are what we call ductile. That means we can make them into tiny wires. They're also malleable, which means that we can pound them into sheets. So a chemical property of metal that we all know is that if we put it with water, there's going to be reaction, typically corrosion, like rust with iron. If we look at our nonmetals, they don't really conduct heat and electricity well. They're not ductile or malleable. They're really actually kind of brittle, and they break pretty easy. They're dull. They're not as shiny as metal is, and a lot of them are gases. That takes us to metalloids. Metalloids are metal-like. They have some properties of metals, some properties of nonmetals kind of combined together. They can be shiny or they can be dull. They're solids. They conduct heat and electricity better than nonmetals, but they're not as good as the metals are. They are ductile and malleable. So when I go and look at my periodic table, the way it is organized, there are families. That's our columns. We also refer to those as groups. So elements that are in each family, they have similar but not identical properties. So if I look at lithium or sodium or potassium, they're all going to be kind of soft, white, shiny metals. If I look horizontally, those rows are called periods. The elements that are in a period, they're not all alike in properties. They change greatly across that row. So let's look at these. So we're going to start by looking at the families. When we look at the families, hydrogen is kept separate from the rest of this. So keep that in mind. Hydrogen is kept separate. So as we go through, each of the highlighted region is what we refer to as one of our groupings. Each of these has a specific name that we are going to learn. So the families on the periodic table are those groups, those columns. It's based on their chemical properties. Each one has a specific name that allows us to differentiate it from the other families. Elements in those families react differently with other elements. So the first one we have is the alkali metals. That would be lithium, sodium, potassium, so on and so forth. We do not include hydrogen. It is a nonmetal. These are soft silvery metals. They are very reactive, especially with water. They conduct electricity. Then we go, so this alkali family is found in the first column of the periodic table. We can cut them easily with a knife. They are highly reactive. They react very violently with water. They are by far the most reactive of any of our metals. They are never found free element in nature. They're always bonded with something else. Then we move over to the alkaline earth metals. We're in the second column. They are never found uncombined. They are also extremely reactive, and that includes magnesium, calcium, so on and so forth. So magnesium, often used in flares. When exposed to fire, it goes very, very bright. So these are white and malleable. They conduct electricity. We find them in flares as well as flash grenades. That takes us to the middle block, this giant chunk in the middle. We refer to those as the transition metals. They are good conductors of heat and electricity. We use them for jewelry and coinage and wiring, and we use them when we build cars. They can bond with a lot of other elements in a variety of different shapes. So when we look at those transition metals, that includes elements in the B families. These are the metals we're most familiar with: copper, zinc, gold, iron, silver, nickel. They are good conductors of heat, good conductors of electricity, and also sometimes used for brightly colored pigments and paints. So leaving the transition metals, we start with the boron family. The boron family is right here. It's named after the first element in the family. It includes a metalloid, which is boron. Everything else is metal. It includes the most abundant metal in the Earth's crust, which is aluminum. So again, big takeaways from the boron family is that boron is a metalloid. The rest are metals. Aluminum, largest one in the Earth's crust. So that takes us to the carbon family. This family includes nonmetal, which is carbon, metalloids, and metals. Now, the element carbon is called the basis of life. There's an entire branch of chemistry that is devoted to carbon compounds, and we refer to that as organic chemistry. We will be studying the basics of that coming up here soon, so keep that in mind. It is coming. So the carbon family is right here in our periodic table. So you may have seen some carbon in the form of coal. Next up, we are in the nitrogen family. The nitrogen family is named after the element that makes up 78% of our atmosphere. That family is going to include nonmetals, metalloids, and metals. So other elements that are in this family, which is this third one over here from the transitions, that would be phosphorus, arsenic, antimony, bismuth. So this group shares electrons to form compounds. Some of them, like phosphorus, are fairly reactive. Obviously, arsenic is considered fairly deadly. Moving over, we go to the oxygen family. Most of the elements in this family are going to be sharing electrons when they're forming compounds. Oxygen is the most abundant element in the Earth's crust. It's incredibly active, and it combines with almost all of the other elements. So that family contains metals, metalloids, and nonmetals. They are very reactive. Not quite as reactive as some of the ones we've earlier looked at. The halogen family, we are second from the right here. The halogen family include chlorine, fluorine, bromine, iodine, acetine. So these are the most active nonmetals. They are never found free in nature. Never. They are used in disinfectants and light bulbs. They are nonmetals. They are reactive and bonded frequently with elements from group 1. So that would be from our very first row right below hydrogen. We'd be bonded with those from that first group. Our last group is the noble gases. These are colorless gases. They are incredibly unreactive. They're very inactive. Their outermost energy level is full. Their electron orbitals are full. Thus, they do not readily combine with anything else, and we refer to them as inert as a result. When we're talking noble gases, we're looking at helium, neon, argon, krypton, xenon, radon. All of the noble gases are found in small amounts in the Earth's atmosphere. So these exist as gases. They are non-metals, they're not reactive, and they make some pretty fun lights when we add some electricity to them. So they are right here in this far right column. And then we start looking at the rare earths. These are the lanthanide and actinide series. So if we look at the lanthanide series, one of these are synthetic. If we looked at the actinide series, most of them are synthetic. So we have to be aware that a lot of these are lab made down here in this block here at the bottom. So these rare earth metals, some of them are radioactive. They are silver or silvery white. Some of them are gray. They do conduct electricity. So if I look at the periodic table, this is kind of based on what they're known for.